Right, welcome to part 3 of our C++ course. Today in this final part we're heading towards more serious science. So we're going to start by looking at pointers, which are a concept actually from back in C, but in a lot of scientific applications you're still going to have to understand them. And then we're going to look at classes, which is a very C++ thing, something that C doesn't have, so we're going to see both extremes. And then we're going to be looking at a library called Armadillo for sort of more mathematical scientific computing, so that gives us some more power. So we're heading towards more scientific computing today. And we're going to start, however, by trying some debugging exercises. So if you look in the debugging folder in the GitHub repository, you're going to see 7 or so scripts, none of which should compile. So my task for you is, can you go through these scripts, try to compile them one by one, see why they don't work, and try to fix it. So have a go.
So to start off this challenge then, here we are down here in part 3, debugging. If you go up to the top of the GitHub repo, there is the debugging folder, and here are, as promised, the 7 C++ files that don't compile. So go through, see if you can fix them all, and I'm not going to go through the answers, but you can find the answers in this text file. Ultimately, if it compiles, you've probably got it right, but you can check here. And then we'll continue with the next section, if we can find it. Where's it gone? There we are. So have a go at debugging, and then come back here. All right, so hopefully that warmed you up and reminded you of some of the pitfalls that you can fall into when doing C++. I wanted to show you one thing before we crack on with the meat of today, which is Makefiles. If you haven't used a compiled language before, then this will look new to you. But you will remember from the previous session that when we were compiling multiple scripts together, we had to use long expressions like this. We had C++ sign function, absolute value, learning function.cpp, when we wanted to use all of the functions from all of these files. And so that's okay, but in practice, it can be a little awkward. So let me show you what I mean. So here is the terminal window. I'm going to go ahead and type in that long command, sign function.cpp, absolute value.cpp, learning functions.cpp, and we're going to output it into sign. And it compiles. Good. Let's just check that it works. Excellent. So this is something from the previous session, so you should be able to do the same. But typing that every time is pretty long, and you're likely to mess it up, particularly if you have lots of different CPP scripts that you want to compile together. So what we do is that we put it in a Makefile. This is a file where you can just basically write out this command and give it a shortcut. So you can just type the name of the shortcut. Let's go ahead and do that. So let's head over to Atom. Here's our Atom window. Let's create a new file. Now, before we type anything in it, we're going to go ahead and save it. And Makefiles have to be called something specific. They have to be called Makefile. So Makefile, no extension, just Makefile. If we go ahead and save it, so there's no .text, .anything. It's just Makefile. So now we've saved it, we can go ahead and use the command. So let's see, this is what we wanted to shorten. So I'm going to go ahead and copy that, and I'm going to paste it into here. But before that, I'm going to give it a name, a shortcut. So we can put multiple sort of strings of commands in a Makefile. I'm going to use the expression make all. So I'm going to use all as the shortcut. So I'm going to type the word all, and then colon, and then on the next line, when we have this expression, we need to tab it in. Right, so you need to place a tab here. And here's a technical point, if your text editor is placing spaces every time you press tab, this isn't going to work. It has to be a tab character, so you have to edit that in some way. All right, just be careful. If you followed my instructions by saving this as a Makefile first in Atom, you will automatically get a tab character here. Just be careful. So we can go ahead and save this Makefile. And now, instead of having to type all of this every time, we can go ahead and type make all, right? So make runs the, looks for the make file, and all is the shortcut. So make all, there you go, it tells you what we're doing, and it's run. Once again, we can run the sign script. Now it's all compiled, and that works fine. Good, so that's just something to be aware of. Most complicated scientific programs will have a make file, and there might be various different shortcuts, because there could be different bits that you want to compile together. Maybe you want to compile with different optimization. Maybe there's a debug version of the code where you want to include some debugging functions but not other. You'll see when you get to play with one of these larger pieces of code. All right, let's head back to the script and let us move on to the next section, which is pointers. So in order to talk about pointers, we're going to have to do a little bit of theory. So let's jump into the theory and then we'll have a play.
Now in the second session we talked about arrays. Arrays are a C++ concept. Back in the old days of C, you couldn't create an array. You had to use a different method of storing lists of data. Some scientific extensions to C++, which you're likely to come across, still use this old-fashioned way of talking about arrays. So it's in that context I want to talk about pointers. Now, when we talk about pointers, we have to think about how information is stored in memory. You can think about the memory of the computer as a line of blocks. When we have a piece of data, let's call it X, we place that somewhere in the memory. So here's our X, and we've placed it in the memory. This is the value of X right there. That's X. But of course, we've placed this somewhere in the memory, right? The computer has to know where this data is being stored, and so we can find in C++ and indeed in C the address of this block by asking for ampersand X. Oh god, that's a horrible ampersand, isn't it? This is the address of X. When you see ampersand, I want you to think address. So this is the address of X. In a moment, we're going to ask C++ to print that out. In fact, let's try that right now.
Here's our new pointers file here. So let's go over to a new window and write this up. Once again, we're going to use a sort of a standard template from earlier. Let's get rid of the bit in the middle. Right, let's go ahead and save this. We're going to call it pointers.cpp. There we go. And here's what we're going to do. We're going to declare an integer, x equals 10. There we go. And we're going to get it to print out the value of x is, and then x. And then we're going to use this new ampersand that we've just talked about. Say the address of x in memory is address of x. And if you pronounce the ampersand as address of, you will never get confused, I promise. So let's try that. You have a go, pause now, and then we'll rejoin. All right, let's have a go. I'm going to clear this, and I'm going to compile. So I'm going to do C++ pointers.cpp. I'm going to output into an executable called pointers. Lovely. Let's go ahead and run it. All right. So the value of x is 10, and the address of x in memory. So this is where it is on my computer. It may well be different on your computers, just where the computer has placed this value in memory. And you've got some hexadecimal number here. The 0x tells you it's hexadecimal, and then this is the address in memory.
All right, so we found this address. Now a pointer is a variable whose value is this address. So we can set up a pointer. Let's call it P. This is a pointer. And the value of this variable P is the address of another variable. That's the idea. P is the address of x, right? That's what we've said. That's P is the address of X, and the value at P, which we write star P, is X. That makes sense, right? P is a pointer, the value of which is the address of X, and then so the value at the address of X is X. That's what we've got going on here. All right, let's get C++ to print that out for us.
So let's now set up a pointer which is going to point at this address. So here we declare the integer. Now let's declare a pointer which is going to point at an integer. All right, so it's going to point at an integer, so we declare it with int and then star because it's a pointer. So we're going to declare a pointer P, which is going to point at an integer. That's why we've written int, and then the star tells us it's a pointer. Then we're going to set P, the pointer, to be, the value of the pointer to be the address of X, right? So now we have the value of X is X, the address of X is at X. Let's go ahead and add the address stored in P. So let's see that it works. So this should be an address. And then let's ask what's the value of star P. Remember, the star is the value at. So the value of the value at P, that address, is star P. So this will be the value at the address that's contained in the pointer. All right, so I'm going to save that, and I'm going to compile it, but first I'm going to give you an opportunity to do just that. All right, let's have a go. So once again, I'm going to compile. Good, and now I'm going to run. So we have the value of X is 10. The address of X is blah. The address stored in P is blah. Well, that's what we wanted, right? Because we set P equal the address of X. There it is. And then the value of star P is 10. So the value of the value at P is indeed 10. P's the pointer. Okay. So now, something for you to try. I want you to, as I say here, see what happens to the value of star P if we change the value of X. Right, so we're going to change X, see what happens to the value of star P. Have a go. Right, hopefully what you found then is if I change the value of X, let's say call it 2, even though I'm not changing P, right, so I'm changing a variable X, but I'm not changing P, I compile and I run, the value of star P has changed. Of course it has, right, because star P is the value at the address in P, which is a pointer, points at X. Points at the piece of memory. All right, back to the theory to talk about arrays.
Now I said historically pointers were used instead of arrays. Let's think about arrays in terms of the memory that we spoke of earlier. So once again, let's think about memory as blocks of data. Let's suppose we have an array which we're going to call primes. Primes is going to be 3 bits long, and it's going to have the first 3 primes in it: 2, 3, and 5, like that. So this data has to be placed into the memory, right? Let's place it here: 2, 3, and 5. And in fact, the fact that these arrays are stored sequentially in the memory is an important fact about arrays. In an old C array like this, the data is stored one after the other, which means if you know where the data starts, you can find the next element of the array just by going one forward in the memory itself. So that's quite an important idea. So let's think about these 3 bits of data. We've got our first piece of data here. This is primes 0. This is primes 1. Remembering, of course, that C is a sensible language, so it starts counting at 0 to 0, yeah. And there's primes 2. So let's once again think about pointers. Now, primes 0 is the value of 2, primes 1 is the value here, primes 2 is the value here. Primes by itself is a pointer value of which is the address of the first element in the array. Alright? So primes by itself is an address, and this is why in some old bits of scientific code you can see vectors and matrices, things that are multidimensional, set up as pointers and pointers of pointers. Let's see this in action.
A new file, pointer_array.cpp. That's what we're going to do. Okay, I'm going to save it before even starting. Pointer_array.cpp. Good. I'm going to copy and paste the general structure from previous script, and we're ready to go. Okay, so I'm going to start by setting up an array of integers. There's that primes 3 we talked about on the little whiteboard. It's going to have 2, 3, and 5, the first 3 prime numbers in it. And then I'm going to set up a pointer, which is going to point to an integer, p, so int star p. P, the pointer, I'm going to set equal to primes. Remember that primes is the address of the first element in the primes array, that address in memory. So we can leave a little comment to ourselves. We're going to set the pointer to point at the start of the array. So let's loop through the array, printing out the address and the value at each case. So let's do a loop for int I equals 0. We're going to go I less than 3 because we're going to go through the array. There's only 3 bits in it. I++, and we're going to see out the address of primes I. So I'm going to replace that I in a second. Is, so then we're going to output P, and the end of the line, I'm going to put I in here, so like that. So I think hopefully she's clear what that does. And then, so that's the address of primes, P, and then we're going to say the value of primes is, primes I is, and then star P. And then I'm going to do plus P. So let's have a look at what this does. So this is setting P to point at the start of the array. And then I'm going to loop through the array, I equals 1, I equals 2, I equals 3. And I'm incrementing I in the array, but P, the pointer, I'm only incrementing here. So I'm going to increase the pointer by 1 every time. If you think about what that means, remember the pointer gives us the address of the beginning of this array in memory. Plus P jumps to the next piece of memory, the next block of memory, which is the next element in the array. So this should be rewarding. So have a go at this, and we'll talk about it once you've executed it. Okay, let's compile. We're going to do C++ point array. I'm going to output it into point array. All right, let's go ahead and run pointer array. So let's have a look at this. So the address of prime 0, the first element in the array, is this. The value is 2. The address of primes 1 is this.
values 3, address of primes 2 is this. Now, for a bonus, I'm not going to discuss this, but have a look at the numbers here and see they're increasing by 4 every time. That might not be so obvious from C to 0. C represents 12, so C for 0 is in hexadecimal is an increase of 4, and this is obviously an increase of 4. So perhaps you might want to think about why it's an increase of 4 and not any other number. Just a little bonus. But this behaves as we expect, so this is good because we're going through the array element by element using pointers. And there are still, as I said, many scientific bits of software. FFTW is probably one of the more common ones, the fast Fourier transform algorithm that still uses this type of pointer array to represent array data, to represent vectors and matrices. So I don't expect you to write anything using pointers, but I do expect you to be able to go away understanding, at least theoretically, how they work, and so you're not intimidated when you come and see them. For a little bit of a bonus, why don't you try seeing what star of primes plus 2 outputs. Think about what that could be, what it means to add 1 or add 2 to primes, and then have a think, have a go, and then let's come back. So here I've typed in what is star, the value at primes plus 2. Well, we know primes is the address that corresponds to the first element in here. So primes plus 2 will change to the address of what? I wonder. Let's see. If I run this again, so once again I compile and run. It's 5. Right? Primes plus 2 has added 2 to the pointer, so now it points at the third thing along, or position 0. Good. All right. We're going to move on now to, that's all I want to say about pointers. Time to move now on to classes. So section 15, classes. Now, classes are one of the main things that separate C++ from C, and indeed most modern programming languages have some idea of classes. Classes are a way for us to set up objects that have properties and functions which are particular to that type of object. So we're going to use a nice classic starter example of setting up a rectangle as a class in our code. The rectangle is going to have a property of its width and a property of its height. We're going to set these properties, and then we're going to work out things like its area, its perimeter, that sort of thing. And let's have a go. Let's have a new script. We're going to call it rectangles.cpp. So once again, I'm going to start by saving. Now, classes are a good way to store information about real-life objects which you are trying to represent in your code. In my own research, I do this all the time. It's a nice way to sort of keep things apart, give access to properties and functions which belong in these classes to certain bits of your code. It makes for neat code, and it is good logic, nice programming. I'm going to once again use the standard outline from an earlier script. All right. So I'm going to set up this rectangle class, so we're going to be able to we're going to create as many rectangles as we want. Every time we create a rectangle, this rectangle is going to have a property of a width and a height, and this makes it really nice. So currently, when we create integers, and integers have properties, or we create floats, and floats have properties. Now we're going to declare rectangles, and a rectangle is going to have its own property as well. So in order to set up this class, we're setting up this class, but we don't do it within the main function, we do it outside. So we're going to set up the class rectangle, and we're going to say the rectangle has some properties. These are going to be public properties, and you can have public and private properties. A public property is one that your code is always going to be able to reach in and edit. So you'll be able to as we'll see in a moment,
change the rectangle's width from the outside. In a moment, we'll also look at making these private so that you can only change them from the inside, creating functions which specifically belong to the rectangle. So let's have a go at this. So we're going to set up a width. This is going to be the width of the rectangle. And we're going to set up the height. So width and height are going to be properties. And that's going to be it. We can put a semicolon there if we want. Inside the main function, let us declare a rectangle rec1. So we're going to declare rec1 to be of type rectangle. And then we're going to specify some things about it. So let's do that. So rec1.height is going to be 5, and rec1.width is going to be 6, like this. No particular need to write it as a decimal, I suppose, but I suppose we can. We can declare area. So here we're going to declare area. We're going to work out the area of the rectangle. Let's do that. Area of rec1. So area is rec1.height multiplied by rec1.width. Now we're working this out outside of the rectangle class of rectangle object, but of course it's a bit silly because area is also a property of the rectangle. So we'll work out how to do that in a moment. So the area of rec1 is going to be this area that we just defined. All right. So this is what is on the GitHub. So either you can type it up or copy and paste, and then let's compile and run it. I'll give you a moment to do just that. All right, let's compile and run it then. We can clear this from before. C++ rectangles.cpp, and we'll output it into something called rectangles. And there we go. Right, let's try it. Area of rec1 is 30, as it should be. 5 by 6 is 30. I can add a space there if we need to, I suppose. All right, so your turn then. I want you to go ahead and add another rectangle, rec2. I'll give you a moment to do that right now. So if you've done that, you should get something that looks like what we've got down here. I'm going to quickly do that in my own script. So we have rectangle rec1, rectangle rec2. We've got this specification here. Control-Shift-D or Command-Shift-D on Atom, if you haven't found it already, enables you to duplicate entire rows. It's quite a nice little function. You see, so I want to duplicate both these. In fact, let's do the top one as well. We're at it. Control-Shift-D does that. And then also, if you hold down Control or Command and click on Atom, you can place the cursor in multiple places and then do everything at the same time. Yeah, okay, I know it's not Vim, but it's still quite neat. All right, I'm going to compile, see whether that works. Brilliant, that looks good to me. Okay, so now let's go ahead and make a member function of the class. So far we have created area, and we've worked out the area outside of the function. Now let's make area a function inside the rectangle class. As it should be, right? Area is something that you should be able to work out, and it is indeed a function. So let's go ahead and do that. So double area, because it's going to return a double, right? So the output goes there. There's no input to area, so we just do rectangle.area, but it's still a function, so nothing inside the brackets, because it's not taking any input. And we're going to ask it to return the width multiplied by the height. Width and height it knows because they're properties already. That is our area defined. So that seems good, I think. Your turn now then is to, as I say down here, Replace the bit where we worked out area, rec1.height, rec1.width, with area equals rec1.area, and see that it works. Once you've done that, I want you to try adding a member function perimeter, which returns the length of the perimeter. All right, so have a go, and then come back. All right, so I'm going to quickly do that. Let's see whether you are able to do the same. So I said replace these bits down here. So instead of working this out and working this out, we can say rec.1, this is rec1.area, and this one here, rec2.area, called like that. Quick compile, let's check. Do we get the same answers? Yep, good. And then I asked you to have a go at doing perimeter as well. So that's going to be double perimeter. And we're going to return, and okay, you had to think about that, but that was not too difficult, hopefully. The width plus the height multiplied by 2 gives you the perimeter of a rectangle. So let's write it here and here. So instead of area, let's write perimeter, and instead of doing dot area, let's do perimeter as well. Okay, let's try that, and how about that? That seems good, right? Because this was 5 and 6, so add together 11, double it 22, and that works for this one as well. Double 22, you get 44. Lovely. So that worked, but we're now going to look at another way of creating a member function. So here, when we created a function, we did so within, up here, we did so within the class declaration. We explained what it, we declared it, and then we said what it is that it does. If your function's more complicated, you might want to put that somewhere else, somewhere neater. So that's what we're going to do. We're going to create a new function, set dimensions, and this function is going to allow us to set the dimensions of the rectangle. So rather than doing rectangle.width, rectangle.height, we're going to use a set dimensions function, which is going to do that for us. And that will allow us to protect width and height so that these can't be edited explicitly from outside this class. So here we go. This is a function set dimensions. It's not going to return anything, which is why I've said it's declared it of type void, because it's going to set the dimensions, but it's not going to return anything. And it's going to take 2 doubles. Obviously, it's going to take the width and the height. However, I'm not going to name these doubles here, and neither am I going to say what the function does. I'm merely declaring it ahead of saying what it does. And if you recall how we declared functions in header files, this is exactly the same sort of idea. So we've declared the class up here. We said that set dimensions is a function that exists, but in fact you can declare it completely outside. So here's how we're going to do that. We're going to declare it and define the function out here. Once again, void. Remember, set dimensions is a function that belongs to a rectangle, so if we are trying to declare it outside of the rectangle class definition, then we have to do rectangle : set underscore dimensions. It's going to take a double x and a double y. Right, that's the width and the height. And we're going to specify that width of rectangle is going to be x, and height is going to be y. Width and height are automatically understood as belonging to the rectangle class here. We know they are here. And that, I think, should work. So in a moment, I'm going to give you an opportunity to compile and check this. Once you've done that, I want you to replace rec1.height equals 5 and rec1.width equals 6 with a call to rec1.setDimensions, and the same for rec2. So have a go at that, and then we will come back. All right, so I'm going to first check that what I've written actually compiles. Remember, I haven't done that yet. All right, so far so good, so no problems. Now I'm going to use a call. So instead of doing this specification, I'm going to do rec1.setDimensions 5 and 6, and the same here, rec2.setDimensions 10 and 12, I think it was. Okay, let's see that that compiles. Oh, I've missed off a semicolon. There we go. Let's try again. Oh, I've compiled it twice by accident. There we go. Good, that looks like that's worked. What we can do now is move width and height out of public and into private. So now width and height are going to belong to rectangle still, but let's cut that all in. We're not going to be able to edit them in the main file. If we want to edit them, we have to use some of these inbuilt functions, set dimensions. So this is a nice way of keeping bits of your code separate. So just to confirm that that works. Lovely. All right. So we've created this nice script. We've got the script down here that sets the dimensions and then looks at the area and perimeter of the rectangles. And we've declared the rectangle class up here and functions that work on it. That's okay, but if we wanted to use a rectangle in lots of different files, we don't want to have rectangle declared in every single one. So let's put the class declaration and this definition of set dimensions here into a header file. So this is a task for you. See if you can remember how to do this from yesterday, or rather the previous session. I want you to put the class declaration and set dimensions into a header file, which we're going to call rectangle.hpp, and then I want you to call it from rectangles.cpp. Okay? All right, have a go. So let's move this top bit to a header file. Not very difficult if you just remember what we did last time. Here we have the class and the function declaration. We're just going to cut that, paste it into a new file, call it rectangle.hpp. There we are. And then we can just include it at the top here. So include, and remember, because it's a local header file, not an inbuilt one, we use quotes, rectangle.hpp. So that looks good to me. Let's go ahead and compile it. Let's clear this. So let's compile. Is it happy? Yep. And let's try and run it. Fabulous. It works. So that's a nice way. I've sort of stepped you through there so you can see the sort of the neat way that you can define classes. That's all I really want to say about classes. If you've got time, you might like to try creating a new class, complex underscore number. I'm not going to talk about it in this video, but you might like to try creating this class and then setting up some functions for adding and multiplying complex numbers. Complex numbers, of course, have a real and imaginary part, so you can think about them similar to what we've done with rectangles. I'm not going to talk about this, but if you're steaming ahead and you fancy a challenge, that's something to have a go at. Otherwise, we're going to move on to section 16, where we're going to be talking about Armadillo. So now let's look at the final part of the C++ course, something that I wanted to show you because a typical scientific programming problem is that whatever system you're looking at some point you're going to be able to represent it perhaps as a matrix multiplied by a vector, as some sort of linear algebra problem. And so you're going to be looking to use some linear algebra library. Now, if you're using something like MATLAB or Python with NumPy, it's pretty easy it's pretty clear how to do matrices and vectors. NumPy is the right library for Python, and MATLAB has this stuff all built in. But of course, C++, was never built directly to do this sort of linear algebra, and so you have to use a library. And there are a lot of choices. Ultimately, the choice of library that you're likely to make mostly depends on which piece of code you get given, maybe what your research group does. I'm going to show you just one possible one. It's called Armadillo. It's a linear algebra library for C++ that I use in my own research. And so I'm just going to show you briefly how you can use this to do some linear algebra problems. Here's Armadillo. I think it's pretty nice. It's being constantly updated. It's a high-quality linear algebra library for C++, giving you commands that look a little bit like MATLAB, so they're sort of easy to understand. Matrices, vectors, tensors, and linear algebra solvers. It's all in there. The nice thing is that it integrates with the linear algebra library that's built into your computer. So all computers, as part of their sort of internal processors, have linear algebra libraries built in, and Armadillo connects onto that. So you get the speed of the linear algebra library at the core of your computer. Okay, so let's go ahead and download the Armadillo zip file, which is in this GitHub repository. You could, if you wanted, you can download it from the Armadillo website. That's fine. I think it's probably easier if you download it from here. If you do that, so the easiest way to do that, here's what you want to download here. The easiest thing to do is to download the entire directory, the entire GitHub repo. If you go up to clone or download, you can download the whole thing as a zip. If you download the whole thing as a zip, then you can open it up. And once it's downloaded, you can open up. Here's the GitHub file, and then I want you to take the zip file here. You need to extract the Armadillo zip file, and then you have an Armadillo folder. It's called Armadillo, then the version number, and if you double click it, you should see all the Armadillo stuff inside. This is important. That's how it should be, and then you can copy and paste that from the GitHub folder into the folder that contains all of our CPP folder, and you can see that I've done that there, and I've placed it there. So our CPP folder, which is sitting in our home directory where we've saved everything, should have this Armadillo folder, which contains all of the bits of the library that we're going to be using it. There are actually different ways when you're installing on the bigger machines on how to install Armadillo. This way works quite nicely for what we're trying to do. So I'm going to give you a sec to do that installation, and then when you're ready, we can go ahead and do some linear algebra. So with that installed, let's go ahead and create a new file, armadillotest.cpp. Here we are. So let's create a new file. Again, I'm just going to use the template of an old simple file. Let's call it, as I said, armadillo test.cpp. And we're going to just going to get it to multiply two matrices together just to start off with. So we're going to include the stream that we, input output stream we already got. We're also going to include Armadillo using these angle brackets. Now the way that we're going to include the library up here, we're going to include it in the path when we compile. So it's going to pretend that it's an installed library, which is why we're able to use these angle brackets up the top. Not only do we use the standard namespace, we're also going to use the Armadillo namespace, allowing us to use Armadillo functions right off the bat. So that's using namespace armor. And then here we go. So we're going to start by declaring a matrix A, mat A, and it's going to be a matrix with some random numbers in it. So let's use randu, mat and angle brackets, and it's a 4x5 random matrix. The same is true for B, mat B equals randu mat 4x5. So once again, this is going to be a bunch of random numbers inside a 4x5 matrix, and then I want to multiply them out together. So it's A multiplied matrix multiplication times b, but of course matrix multiplication, you will remember the inner two dimensions have to be the same. This dimension has to match this dimension, so we can do a times b transpose, that's b dot t with the round brackets, and then we get to end the line. That's it. Now I appreciate that this is slightly awkward notation, but once you're over that, I think this is surprisingly neat for C++, so I think this is good. All right, and this covers a whole multitude of sins, right? We're multiplying two matrices together. Let's test that and see whether it is going to work. So here we go. So once again, C++, Armadillo test.cpp, and we're going to output it into Armadillo test, but we have to be careful before we go ahead and compile, because we need to link in that Armadillo library that we've already said is there. So to do that, dash capital I, and then the full path to the Armadillo library. There are better ways, to be honest, of installing libraries, but this works for us because it's neat and we can pop it in the folder that we're working in. But here we go, we're going to include the library explicitly. So if you've saved all your CPP files in the same place that I have, it's in your home directory /cpp/ and then the name of this folder here. So that's armadillo 9.870.2 /include. But we're not done, so don't press enter just yet. Remember I said that the nice thing about Armadillo is that it links in with the linear algebra software that's already inside your computer. It's inside the processors. So we have to link to those as well. Now, whether this works or not on your system depends a little bit on how you've got everything set up. If you're on a Mac or on Linux, this should just work. On Windows, I'm not so sure. But if it doesn't work, that's okay. If you're happy to watch and not try it yourself, or try again on a different machine at some point, or indeed, you may well be able to get it to work, but you're going to have to look up the instructions. But that aside, and with that caveat, we have to include the link to those to those inbuilt libraries. So that's LAPACK, so it's -L and then LAPACK, LA for linear algebra. And also we're going to link to BLAS, so -L, little l, and then BLAS, BLAS. On a Mac, if we do that, it should compile. Nice. And then we're going to try and run armadillo_test. So we should see two matrices multiplied by each other. There we go. That's the answer. Is that underwhelming? Maybe. But you're welcome to have a go at that now. And then we're going to go ahead and have a look at a linear algebra problem. All right, so we're now going to move ahead onto a linear algebra problem. We're going to solve this system of equations here. Why is this a linear algebra problem? Well, so let's go and try and solve this set of simultaneous equations. Remember that the way that we solve these equations, because it's a linear set of equations using matrices, is that we pick out the coefficients of x, y, and z. Here's the set of coefficients: 1, 2, 3, 0, 1, and 4, 5, 6, and 0. So we pick those out and we put them in a matrix. So that's again 1, 2, 3. Oh, that 1 wasn't very convincing. 1, 2, 3, 0, 1, 4, 5, 6, 0. And then we multiply that by the vector x, y, and z. And we say that that's equal to the vector on the right side, -1, 0, 1. And remember that the rules of matrix multiplication allow this to work, right? When you multiply a matrix by a vector, or a matrix times another matrix, then you multiply across and down, so you get 1 times x, 0 plus y, plus 5 times z. That gives you the top line. And then you describe these three mathematical objects separately. And let's call this matrix A.
let's call this vector in the middle capital X, and then on the right hand side we've got this vector b. And so we have that a times x equals b. And using linear algebra, we could therefore go ahead and say that x, which is what we're after, is the inverse of a multiplied by b. So that's an inverse there. All right. So how do we do that using C++ and Armadillo? In MATLAB, this would be easy. Is it so easy in Armadillo?
So we've got our matrix A, that's a set of coefficients here. We've got a matrix B, which is what's on the right-hand side. Our question is, what is X, the X, Y, and Z in the middle? So we're going to try and represent that using Armadillo's structures. So I'm going to, once again, let's save a new file. I'm going to call this Armadillo equation. I'm going to call this Armadillo equations.cpp. All right, and okay, so our matrix A, mat A equals, and then there are different ways of initializing matrices. In fact, you can spend all day enjoying the Armadillo documentation. There's a lot of good stuff in here. Let me quickly show you. So here we have matrices, different types of vectors, all sorts of things you can do. And you can initialize a matrix in all sorts of ways using different matrices, vectors, rows and columns. One thing that you can do as well is that you can explicitly say what the matrix is using a string. That's what we're going to do now. This looks like MATLAB style notation. So mat A equals mat, and then in quotes we're going to write out this the matrix A that we just saw. So that's 1, 0, 5, 2, 1, 6, 3, 4, 0. So in MATLAB style notation, so that's 1, 0, 5, semicolon 2, 1, 6, semicolon 3, 4, 0. And we're going to have a matrix on the right hand side, which I know is a vector, but is a matrix with just one column. So that's -1, 0, 1. And then the matrix we want to solve for is x. We don't know what that is, so we're just going to declare it. And then x is solve of A and B. Remember that given that we want to find A inverse times B, you almost never need to compute A inverse. In most problems, better to let a solver do it for you, and that will use a much more efficient algorithm. So hopefully that will solve our system for us in the most efficient way it knows how. See out X and end the line. So that's Armadillo equations. Let's go ahead and try to compile it. So I'm going to edit my previous statement. Armadillo equations into Armadillo equations. Will it compile? Once again, we need to make sure that we've linked in layback and BLAS. So far, so good. If you've been able to compile it, why don't you go ahead, see whether it runs now, and then come back to the video. All right, let's try and run it. Armadillo equations. Hey, look at that. We have a solution, 19, -14, and -4, which means that in our x, y, and z, x was that first one, 19, y was -14, and z was -4. Fabulous. So that was our little demonstration of Armadillo. Hopefully installation wasn't too difficult, but you can see that in order to get the power out of the machines, we need to tie into the internal processors. That's what those links to layback and BLAS were all about. So that's Armadillo. There are other linear algebra libraries. Eigen, I think, is relatively popular. You can pick what you like. Depends on the problem that you're interested in, but Armadillo is one that I use. All right, so as we head towards the end, let's just talk about the last few things to think about. There are plenty of libraries. There are way more. If you want to use complex numbers, the complex library is there for you. One good use of C++ and one thing that I use it for is parallel processing. And there's a lot to learn from OpenMP. I don't think we have a course on it at the moment, but we might. So keep an eye out for that. OpenMP allows you to control what each of your processors are doing when you send your code to on the big cluster machines that we have in the college. So that's really nice. Also, I sometimes use CUDA, which is used for GPUs. So C++ interfaces nicely with that. CUDA is another sort of library and language that you need to attach, it's a library for C++. So another thing for you to learn and bolt on. That's all open to you and all good for scientific computing. The last thing to show you is the optimization parameter here in number 16. When we've compiled these programs, we've done so with C++, the name of the file, and then -o to say where we're going to send the output file, hello, and that's all good. There are optimization flags in the compiler where you can specify that I want to spend more time compiling, but I want a more optimized code, so it's sped up a little bit. So this takes longer to compile, but you get faster code. For most production code, you want to use the flag. So here we have C++ hello world.cpp -o hello, remember that. Boy, that's taking us back, right? C++ hello world.cpp into hello, remember that? Does it still work? It does. This time I want to compile it with -O, so it's not a 0, it's -O for optimization. O3 is the highest level of optimization. It's O1, O2, O3. O3 is the highest -O. Now it's compiled with the highest optimization. We can still run it. Not that we can see any speed difference for something so simple, but for your more complicated programs, that's what you would like to do. So that rounds up our little C++ course. Hopefully you feel that this has given you a good introduction to all of the things that C++ can do. You've seen a lot of the syntax, you've had a look at the libraries. Today in particular, we've spent a little bit of time looking at Armadillo here. But we also spent plenty of time looking at classes, and we looked also at pointers, which are important in understanding how C and C++ control their memory. A lot of big libraries for C++ still use pointers, so something to know. Right, so that brings us to the end. The last thing that I need to do, the last thing that I need to ask you to do is to fill out the feedback form from the graduate school. So the graduate school should have emailed you a link to the feedback form for the course. This is super useful for us. We get to see what you think, and it means that the next time that we do this, we can optimize depending on your comments. So if you can write something in there, that would be fabulous. And as I say, I hope that you found this a nice introduction to C++, and you feel more confident now. I hope that next time you look at a C++ file, you can, I'm just scrolling up to the top, you can feel more comfortable looking at it. You can see, right, I understand what these header files are doing. I understand, what this class is. I think now that you're over that barrier, everything else should be much more simple. You've been able to write a C++ program. Now you can understand and edit more complicated programs. You've seen errors. We've done a bit of debugging. So you shouldn't be intimidated by that either. Hopefully, as I say, you feel confident and happy to go on and learn some more C++ and play with this very exciting language. So once again, thank you very much. Don't forget to fill out the feedback form, and I hope that you will join us for another graduate school programming course.